Hello friends, in this video we will talk about hemoglobin. So first, biosynthesis, catabolism and the functions of hemoglobin. Let's see the biosynthesis. So first step, this is to show you glycine plus succinyl-CoA on delta ALA synthase, release of CoA-SH will get alpha amino beta keto adipate. This is intermediate, okay? It's optional to remember this intermediate, okay? On the same enzyme, but there is decarboxylation to form delta ALA or delta amino levulinic acid. Now let us continue further with the steps. Two molecules of delta ALA will combine. By release of two water molecules will get PBG. So PBG, now four molecules will combine of PBG. Release of four ammonias will get UPG3. On decarboxylation, CPG3. Then on oxidase, oxygen to CO2, NADP to NADPH2 will get PPG3. Then PPG3 on oxidase, release of 4H plus triple P9, protoporphyrin 9. Then on heme synthase, iron is required, will get heme. Heme combines with globin from the amino acid pool. What is the amino acid I told you? Histidine will get hemoglobin. Now catabolism, okay. So in the macrophage, hemoglobin is broken down into heme and globin, okay. Globin enters amino acid pool. This heme on oxygenase, there is a release of iron and carbon monoxide, NADPH2 to NADP plus will get biliverdin. Biliverdin on reductase, NADPH2 to NADP plus, this should come when reductase is mentioned. Will get bilirubin. Then in the blood it forms complex with albumin. When it enters the liver, dissociation of albumin. Then bilirubin on glucuronyl transferase, 2-UDP glucuronate to 2-UDP will get bilirubin diglucuronide. Why diglucuronide? Because two molecules of glucuronic acid, okay? Right. And this bilirubin diglucuronide is going to enter into the intestine or the kidney. In the intestine, through the feces, stercobilin will be excreted. Through the kidney, urobilinogen will form the urobilin, and that is excreted in the urine. So now we will see two main functions of hemoglobin, respiration and buffers. Let's start with respiration, the exchange of gases. So in the lungs and tissues now. In the lungs, oxygen enters the lungs, binds with every molecule of iron in the heme. Then the free oxygen is entering the tissues, combines with myoglobin, that is MB in short, will get MbO2. From that the free oxygen comes out, utilized by the tissues. CO2 from the cellular respiration combines with the hemoglobin to form carbamino hemoglobin. From that the free CO2 enters the lungs, and then from there it will be released out. Now how it's connected with hemoglobin, let us see. First in the tissues, then the RBC, then in the lungs. Now in the tissues, water plus CO2 and carbonic anhydrase will form carbonic acid. Carbonic acid dissociates to form bicarbon H plus. H plus forms 4O2, okay. First hemoglobin combines with this and then this, okay. Reversible, that is in the RBC, now in the lungs. What I told you for tissues, exactly opposite in the lungs. But just remember one difference. In the lungs here, CO2 will be exhaled. That's it. Now let us see with chloride shift or the Hamburger's phenomenon. Okay, actually here you are seeing reverse chloride shift. But first I will explain the actual chloride shift. So what is happening? Chloride is entering from the plasma into the RBC. And now CO2 from the plasma into the RBC combines with water by carbonic anhydrase to form carbonic acid. This will dissociate into bicarbon H plus. H plus combines with hemoglobin to form HBH. Okay. So bicarb comes out into the plasma and chloride goes in. Now exactly reverse what happens in the lungs. Okay. Let's see the difference. The respired oxygen combines with hemoglobin in the RBC to form oxyhemoglobin and H plus. H plus will continue its job. Oxyhemoglobin remains as is. H plus combines with bicarb that has entered into the RBC. Chloride goes to the plasma. Okay. So bicarb and H plus forming carbonic acid. On carbonic anhydrase, water plus CO2 is formed. Then CO2 is respired out through the lungs. Now let us see with the buffers. We will see three main buffers: bicarb, phosphate and protein. Before that, a small introduction regarding the buffers. Buffers is a combination of weak acid and conjugate base. And please note that even the converse is also true. Here we will see bicarb, phosphate and protein buffer in detail. First, bicarb buffer. So the weak acid here is the carbonic acid. Conjugate or the strong base is the bicarb ion. This is how the dissociation happens. So the buffers will depend on law of mass action and Henderson-Hasselbalch equation. So first I'll show you the law of mass action. So law of mass action states that the dissociated reactant, the ratio of the dissociated products to the undissociated reactant is constant, and that constant here is Ka. So Ka is equal to product of H plus and bicarb ion by carbonic acid. Let's apply the bicarb buffer to Henderson-Hasselbalch equation. Okay. So here actually Henderson-Hasselbalch equation tells pH, pKa, the ratio of the salt by acid or the base base by salt or acid by salt. Okay. Here pH is equal to pK plus log of bicarb ion by carbonic acid for bicarb buffer. Let's substitute the values. pKa is 6.1, bicarb is 24, normal is 22 to 26, carbonic acid is 1.2, which is at its normal value. Substituting all of this will become 20. So 6.1 plus log 20. Log 20 is 1.3. You might be wondering how this happened. I'll tell you a way to get this 1.3. So please remember this formula. Log AB is equal to log A plus log B. AB is 20. So 20 is 2 into 10. So we have log 2 plus log 10. Log 2 is 0.3. Log 10 is 1. So at this juncture, I would like to recommend you to remember all the values of log, especially log 1 to log 10, because it will be very helpful when we do the calculations of the acid-base balance. Okay, because acid-base balance is going to involve log, and I would like you to know this log 1 to 10 very thoroughly, and also some formulas related to log. Okay. So anyway, log 20 is 1.3. So sum of this will be 7.4 exactly here. So is the left and right hand side equal? Obviously equal. So what does this tell us? This tells us that at a pH of 7.4, this buffer is strong in the hemoglobin. This is important for alkali reserve. Alkali reserve is important for bicarb buffer. It is the effective buffering of the H plus ion so as to maintain the body pH. And if this body pH is maintained, the metabolic processes will happen normally. There won't be any acidosis or alkalosis. No question of that. Okay. Also, the important point in alkali reserve is to maintain the ratio of 20/1. Okay. Yeah, if we compare with phosphate, it is 4/1. I'll tell you how to get that 4/1 in just a moment. Okay. So this is regarding the bicarb buffer. Now phosphate buffer, weak acid, trihydrogen monophosphate, conjugate base, dihydrogen monophosphate. So let's see the dissociation in 3 steps now. Trihydrogen phosphate becomes dihydrogen phosphate. So di becomes mono. So this is the monohydrogen phosphate. It will become H plus and phosphate ion. You are seeing the charges are increasing in the phosphate molecule. Here it is 1, here 2, here 3 in negative. Okay. It's a negative charge. Okay. And also the pKa is increasing. You can observe. Okay. And now, so if we have to put it in the Henderson-Hasselbalch equation, this is the ratio I want you to put. Na2HPO4 by NaH2PO4. Okay. So let's see with the Henderson-Hasselbalch equation. So we substitute pKa as 6.8, pH as 7.4. Take the difference of these two numbers. You are getting 0.6. Okay. That is log of salt by acid. Antilog of this will be 4. So 4 by 1. Bicarb buffer compare 20 by 1. Okay. Lastly, we have the protein buffer. So protein buffer. What is the structural unit of proteins? Amino acid. So obviously this buffer has to depend on some amino acid. What is that amino acid? Histidine. What is the ring in histidine? Imidazole ring. So shouldn't it depend on the imidazole ring? Absolutely yes, it has to depend. Okay. So it should depend on the ionization constant of the imidazole, that is actually 6.7. To be frankly speaking, it is 6.7. Okay. So protein buffer depends on what? The imidazole of the histidine, which is dissociating at a pKa of 6.7. So that is regarding the functions of hemoglobin. References from where I took the pictures. That brings us to end of the video. So thank you so much. I'll see you in the next video.